Niagara Falls. Well, the story goes that there is a sign on the American side of Niagara Falls that says 150,000 gallons per second of water go over Niagara Falls. It's 150,000 gallons. Now, given what we've said about uncertainty, where is the level of uncertainty? It's not in the ones or the tens or the hundreds place. It's not in the thousands. It's actually in the 10,000 place. So this is actually plus or minus 10,000 gallons per second that goes over the falls. Now, as the story goes, if we go over to the Canadian side, there is a sign that says 567,810 liters per second go over the falls or flow over the falls. So where's our uncertainty here? Well, it's not in the ones place. It's actually plus or minus 10 liters. So we've got a plus or minus 10 liters per second. So a liter is a smaller unit of volume than a gallon, and then again, time is measured in seconds. So how can we equate going from plus or minus 10,000 gallons per second to plus or minus 10 liters per second? Is there anything in your mind that says that that is a reasonable comparison in terms of levels of uncertainty? And the answer to that is no. And it's covered in an area of mathematics known, or measurement known as significant figures. Okay? And so let's take a look at that. So then in this comparison, there's an inherent uncertainty in the initial measurement that implies an approximate flow of either 140,000 to 160,000. That's plus or minus 10,000 gallons per second. How can you then convert your original measurement to a number that is plus or minus 10 liters per second, which is about the volume of the average toilet tank? And the answer is there's no reasonable way to do that. So it's what we call a misuse of significant figures. We have rules for counting significant figures. Now, first of all, significant figures only matter when we measure things, and that's because of the uncertainty in the measurement. We always have a digit that is uncertain in a measurement, and when we do math with those measurements, that gives us a problem in the ultimate solution that we come up with a problem based on the worst measurement we have. So a few rules. Here we go. All non-zero digits, any digit that's not zero in a measurement, we count as significant. So 1, 5, 9, 2, 3, 4, 5, 6, 7, 8, those are all significant. So if a digit is not zero in a measurement, it is automatically significant in that particular measurement. Zeros between non-zero digits are significant. So here are two non-zero digits. I've got a 5 here and a 7 here. Anytime you have zeros in a measurement that are between non-zero digits, these zeros are significant. Okay, so that's a rule that you need to be aware of. Zeros to the left of the first non-zero digit are not significant. So all of these zeros right here, these guys right here, all these zeros are doing is they're telling you about the magnitude of this particular measurement. You will do in chemistry measurements that have very small values in terms of their magnitude. Given the way that you express that value, 0.00027, there are really only two significant figures in that measurement. In fact, writing this in scientific notation would be an easier way to make this distinction. But you just need to remember these zeros are not significant. So I move the decimal place 1, 2, 3, 4 places. So that would be 2.7 times 10, and this is a number less than 1, so that's a -4. So this measurement would be better expressed in scientific notation. However, this is totally legitimate. It's just you have to remember those zeros are not significant. Zeros that fall both at the end of a number and to the right of the decimal place are significant. So while these zeros in front of the first non-zero digit are not significant, this 0 is a significant digit. So this number actually has 3 significant figures, and sig fig is usually the way that we designate that. You might also just see that written as 3SF, standing for significant figures. So zeros at the end of a number and after a decimal place, these are considered significant zeros. That's part of your measurement right there. When a number ends in 0 but it contains no decimal point, the zeros could be significant. They may or may not be significant. So it's best to assume that a number written in this fashion only has 2 significant figures. These are both non-zero digits, so you know they're significant. I don't know whether those zeros are significant. Now, if I place a decimal here, while that is a pretty terrible practice, just applying the decimal place after those zeros, I can make them significant, but that's a pretty not a very good way to write a value like this. If I don't intend for these zeros to be significant, I would be much better off just moving a decimal right over there and writing this as 5.2 times 10 to the third. That's a much better way to write that value if my intention is to only have 2 significant figures in that number. Okay, so which of the following numbers has 3 significant figures? Well, we know from the rules that zeros before the first non-zero digit are never significant, so this only has 1 significant figure. This number, these zeros, are not significant for the very same reason. They're before the first non-zero digit, but this 0 is significant. So I have 1, 2, 3 significant figures. This 0 is significant. It's to the right of a non-zero digit and a decimal place, which makes it significant. So 3 sig figs, and that would be the answer to our question. Let's go on. I don't know whether these zeros are significant. This could be exactly 100, but these zeros it's unknown as to whether they're significant, so I choose not to count them for certainty's sake. So there is only 1 significant figure in this particular case. When you have scientific notation, these are going to be where your significant figures are. This 0 is after a non-zero digit and a decimal place, so it is significant. So we have 2 significant figures. You don't worry about the exponent in this case. And all 4 of these digits are non-zero, so this is 4 significant figures. Significant figures in calculations, multiplication and division. Let's take a look at the rule. The result must be reported as having no more significant figures than the measurement with the fewest total number of significant figures. So both of these are measurements, and I'm going to do math with these. Well, if I look at this number, I have 1, 2, 3, and this 0 is significant, so there's 4 significant figures here. This 0 is not significant, but this 0 is significant. It's to the right of a non-zero digit and a decimal place. So there are 3 significant figures. And so my answer in multiplication and division, this would be the same as if this were a division problem. Although the answer would be different, my solution would have 3 significant figures. The multiplication and division rule is different from the addition subtraction rule. People get that confused all the time. So this is the harder rule. And it says that the result should be reported to the same number of decimal places as that of the term with the least or fewest number of decimal places. So in this case, I do have 4 significant figures in this measurement, but I only have 2 decimal places. So there are 2 decimal places. And in addition, subtraction, those decimal places are going to govern how many decimal places that I can report my result to. In this measurement, I have 3 significant figures, but I have 3 decimal places. And 2 decimal places is fewer than 3 decimal places, so my result can only have a maximum of 2 decimal places. Now, those are the rules for significant figures which drive people crazy. Work on them. Make sure you know how to distinguish between multiplication and division and addition and subtraction rules. They are different. All right, let's go ahead and work a simple problem that has both a division and a subtraction in that particular problem. So we actually have 2 different significant rules that apply. In the particular case, we have a numerator that's 8.81, and we're going to divide that by the subtraction of 16.1 minus 8.44. So we can go ahead and we can simply drag the 8.81, which will divide by the result of this subtraction. When I do the subtraction of 16.1 minus 8.44, I realize that the subtraction rule says that I can only report this denominator to the fewest total number of decimal places that I have. I have 2 decimal places here, and I only have 1 decimal place here. So appropriately, based on the addition subtraction rule, I should only have 1 decimal place. However, if I were to round before I got to my final result, I would get a different answer. And it won't always be the case, but it's certainly the case in many problems that you can accumulate what we call rounding error. So there's a little trick that you can do when you're working these problems. I know that I really only have 1 decimal place in this result because of the subtraction rule. So when I subsequently do my division into 8.81, I only have 2 significant figures in this denominator. But I don't want to round to 7.7 because I might have a rounding error that causes my result to be different than it would be if I went ahead and kept that extra 6 in my calculator and then rounded to 2 significant figures at the end. So I'm going to go ahead and do this division without prematurely rounding, and let's see what we get. 8.81 divided by 7.66. So my answer is 1.15. Hold on, I only have 2 significant figures to deal with, so my answer can only be reported to 2 significant figures. So my answer is actually going to be 1.2 because this 5 is great. It's 5 or greater. I tend to round up, and so that rounding rule is telling me that my answer is 1.2. Well, what if I had prematurely rounded? Let's say I had taken my 8.81 and I had gone ahead and rounded this up to 7.7. And if I round this up to 7.7, I now get a different answer of 1.14. 4. I still have to round to 2 significant figures, and so now my answer, because this is less than 5, is going to be 1.1. So I have a different answer because I rounded prematurely. So what you need to do is avoid rounding prematurely, but keep track of the number of significant figures in each operation and only round when you get to the end.